have various data types, various data levels. You know, and a lot of it's based on when the data was acquired. So it sort of has a spatial and temporal component to it based on the acquisition footprint, which doesn't lend itself well to time series analysis, like you say, because you have to crack open, or if I want to look at time series in a particular spot, I got to crack open 1 million files that contain that spot and look across the thing. So the answer to your question is yes, we're starting to look at some of that. Like how can we better organize the data or optimize the storage to enable the analytics in sort of a cloud-based environment without having to duplicate the entire archive 2 and 3 and 4 times, because the manner in which you analyze it is going to really depend on what your use case is. Like what are you looking at? So you want to identify, you know, what people are trying to do, because a lot of this data is stuff that people aren't going to analyze. You know, a lot of the volume are lower level data that are just used to make the higher level products. So obviously you can ignore that, a lot of that stuff. But then you have to identify, okay, and so you can scope the problem. How do you figure out what people are doing? So one of the things I want to do at Langley, at least with our users, is try to kind of start the conversation with the scientists, because this amazingly, we have all these surveys and things like this to try to get at what people are doing, or what they need. And what they tell you they need is, I need a big pipe so I can download 50 terabytes of data. And I just want to change the conversation with, like, no, what are you trying to do? Like, what's the analysis? What is your process? Like, what answer are you trying to get at? Because then you can start backing out of that. How you can better optimize your storage, which data sets you do it, and what the architecture should.
That's a great summary of, I think, what we ought to be talking about. Not the big pipe, but how we get the big pipes to serve products.
The trick is to pull the data you need out, not have to move the whole
Exactly.
volume.
That's right.
All right, let's leave it there then.
Well, just one more question. You talked about hardening Amazon.
Hardening what?
Hardening Amazon
Okay.
for security.
Yeah.
Have you got a paper or something on that? Because we're trying to do the same thing, and I'd rather not replicate.
Yeah, well, I did on the paper, and this has all been very kind of NASA internal. So the goal has been to come up with a platform that meets NASA specific security requirements for public-facing applications. I'm sure the NGA requirements, because it's from a security point of view, it's not high. It's like a moderate to a low, and even that took us 1.5 years to get everything together.
That's my concern. Trying to meet IC requirements for Amazon is going to be challenging.
Right.
But any lessons learned would be greatly appreciated.
Okay, sure. Yeah, that project's been passed off to to a system architect now. I can see if he's planning on doing a white paper on it.
Cool. Thank you.
Yeah.
So that was the first of 2 presentations about obtaining big data, obviously focused on imagery and satellite imagery and the like. We now turn to streaming of data from a variety of different sources, and hoping probably a little more heterogeneous than imagery from satellites. And for that, we have invited Professor Fox from Indiana University, and some results that they've recently come up with through a series of workshops. And if I can operate this, there we go.
Thank you.
The monitor, is that on the right one, John, or is it on the, do I need to? Still seeing the summary from the last one.
You also have a chat.
The chat, sorry, Jim. Deal with, let's see what we got here. The chat message, it says, really? I got no chat. You guys see that? You don't see that. Current state of the art future. Oh, yeah. Under questions, sorry. I don't see that. No. Huh. All right, well, I will look at that and we'll deal with that. John, can you confirm you see this slide? Did we lose connection?
didn't open it.
Alrighty. We're getting close. It's only 6 more steps. That didn't work, huh? Oh.
There you go.
Hey! Sorry about it. Please.
All right. When do you want me to stop? Give me a time.
Let's go until 5 after, so 25
You know, I'll just cut it down to.
Yeah.
Just tell me when I have, say, 5 minutes.
Okay, all right.
Thank you. All right, so thank you very much for inviting me. I feel a bit harried having survived this morning, Delta, Uber, and now go to webinar. That's very stressful.
It's a modern life, man.
That doesn't sound.
There we go.
All right. So I'm going to discuss about a few things, including quite a lot on streaming. And I believe that you're trying to design some geospatial big data architecture.
In an open, interoperable, loosely
That's right.
coupled fashion.
That's right. Those words are later on. So I'm going to discuss very briefly three inputs to that. One is 2 streaming workshops that we held, which I'll start with. Then the work we're doing with NIST, which has, I believe, some relevance to this. And then very quickly, the work I'm doing myself. So we had these workshops where NSF, DOE, and the Air Force are funded. They were held in Indianapolis and Washington. And they're called Streaming 2015 and Streaming 2016. And there is a reasonably good website, streamingsystems.org, which has everything we did at those workshops. And the first one was essentially NSF funded, and it was in response to a Dear Colleagues letter to try to identify what infrastructure NSF should deploy to support streaming. The next meeting was largely DOE focused, and it was particularly apparent because we looked at DOE applications. And they had 43 to 49 attendees and 20 to 30 white papers each. So they were pretty active. And they had both academia, government, and industry. So here is some summary of what those workshops did, and that is very impressive. I assume Amazon delivered that microphone order just fine.
Maybe that'll help a little bit.
Do you want me to hold this?
That'd probably be good.
All right.
There we go.
Actually, while I'm doing this, I'm going to change my places. This is in between my 2 pairs of glasses.
Another modern gem.
Anyway, all right. So this one is perfect. Fine. So, if we looked at the first workshop, which is completely finished, it has a final report and so on. It had various things in it, including classification of applications. And I guess one key feature of this field is that it is not very well studied. There is very little agreed consensus. I mean, there's work in this field, but there isn't so many. Whereas, for instance, if you want to do high-performance supercomputing simulations, it's not trivial, but it's very well understood what the issues are. It is not very well understood what the issues are here. And if you look at applications, it's not even clear what the important application features are. And that's particularly relevant because industry has some pretty good software. Because streaming data is very important for e-commerce. There's a famous system called Kinesis from Amazon. Google has a product called Millwheel. And Microsoft has an event system as well. However, what are those doing? Those are largely processing ads in real time so that you get the most perfect web page, guaranteed to make you spend as much money. And it's not so clear that that's actually what a very good representation of science. In particular, see some of the obvious science data, such as what we just heard of, images. There are lots of science, like DOE has all these light sources. They pour images into computers, and of course NASA will have satellites and remote sensing and things like that, which are also streaming images. That type of work, now that work is actually done commercially in things like connected car, self-driving cars, that also streams images, but it's not so clear. There is no very clear understanding of what's needed, and none of the talks we had were about processing autopilot or whatever. I mean, Tesla's autopilot or something like that. They were from the e-commerce area. And if you look at the software, obviously everything works, but again, there is, especially academically, there is no strong consensus high-quality solution. There are high-quality commercial solutions. So one activity that is needed is some requirements analysis to see what's going on. So here is a set of the types of applications we looked at. There is a project started with NSF and now with the Air Force called DDDAS. We obviously have the Internet of Things like Twitter and e-commerce. We have here satellite and airborne monitors, astronomy, light sources. The Large Hadron Collider is essentially streaming. It actually tends to be processed in batch, but obviously the accelerator is taking streaming data. There is streaming data used for data assimilation. A lot of the interest of DOE is the fact that their simulations produce huge visualization outputs, which are also effectively streaming, because you're in real time, you're producing new results. And then finally there is control, which of course is probably the self-driving car is soon to be the best example, but obviously control, there's a very aircraft control and things like that, and that's all streaming data. So it's a pretty rich area. Now if we look at things that need to be done, so the pretty important area is algorithms, because there is a lot of computer science work on what's called online algorithms. Those are algorithms which accept data, look at it and make a decision and do something with it and then throw it away. So they're always linear in the problem size. Whereas if you look at most offline algorithms, they're not linear. If you take some classic, say, clustering algorithm, it's actually order n squared for endpoints. And there are also methods which, because some of these sources have so much data, you need to do sampling. And so there is a lot of research. There are essentially no deployable modern algorithms in this field. Then we have in the programming models, we really have three sets. There is the rather ad hoc collection of academic solutions There is the commercial solutions such as Kinesis is probably the best known. And then there is Apache solutions. And the Apache solutions until recently were a little old because Apache Storm, which is I believe certainly what we used and the best of the Apache systems, has just got replaced by Heron, which is Twitter's latest system. And Google has just released Cloud Data Flow, which is now Apache Beam, and that supports streaming as well as batch. And if you look at these famous systems like Flink, Spark, and Hadoop, they differ in their support of streaming. Spark supports streaming in batches. Flink is intrinsically streaming. It's like Heron. Heron is only streaming. Flink is batch and streaming. And Hadoop doesn't do streaming as far as I know. It's not trivial. So let me skip that. All right, so what do we do? So there are no obvious set of benchmarks. If you look at these famous big data benchmarks, of which there are many, Big Data Bench is one of them.